Hello. All right, it is time for our last session, session 8. And our first talk for the session is improved MPC algorithms for MIS matching and coloring on trees and beyond. Our speaker is Se-Jin.
So I'm going to talk about massively parallel algorithms on trees and more generally on sparse graphs. So I'm Se-Jin. This is joint work with Mohsen Ghaffari and Christoph Grunau. So we'll be working in the MPC model. I will skip the definitions. In this work, we'll mainly focus on the strongly sublinear memory regime. That is, each machine has local memory n to the delta for some constant delta smaller than 1, where n is the number of vertices in the input graph. So let's first look at the maximal matching and the maximal independent set problem. So previously in this memory regime, for general graphs, the best algorithm for maximal matching and MIS runs in root of log n rounds. And there is also a conditional lower bound result, which is omega of log n round. So we can see that there is still a large gap between the upper bound and conditional lower bound. And recently there has been some research on solving maximal matching and MIS on special graphs. So there is a previous result. So on trees, we can solve MIS using log n cubed rounds, which is better than the best algorithm for general graphs. And later there is an improved result which can solve MIS and the maximal matching in log n squared rounds for a more general class of graphs, the bounded arboristic graphs. So the arboricity of a graph is a parameter that characterizes the sparsity of the graph. So if the arboricity is small, then the graph is sparse everywhere. And in this work, our main contribution is to improve the previous algorithm for MIS and maximal matching on bounded arboristic graphs. We quadratically improve the previous round complexity. So our complexity is log n rounds. And we remark that this algorithm matches the conditional lower bound for maximal matching because that lower bound holds even for trees. Okay, our second result is about vertex coloring. So we can full color a tree using log n rounds. Okay, so now I'll briefly talk about our techniques for the first result. So our result is based on the previous framework of Beknejad and others. So their algorithm has 2 steps. The first step is called a degree reduction. So they find a matching or an independent set such that after we remove the matching, then the remaining graph has low degree. And then we can use the Ghaffari and Uito algorithm to solve the remaining low degree graph. The bottleneck of this algorithm is the first step, which takes log n squared rounds. And our contribution is to improve this first step to log n rounds. So, so our main technique is a kind of pipelining. So previously, their algorithm has log n phases where each phase has log n MPC rounds. So in total, this is log n squared rounds. So we use a kind of pipelining to reduce the round complexity to only log n rounds. And the main challenge in this pipelining is to analyze the total memory of our algorithm. we want to keep a global memory within near linear. So this is the main challenge. And I'll skip all these details. Okay, so to conclude, our key idea is to use pipelining to reduce round complexity while keeping near linear global memory. So we have some open questions. First, does our technique have other applications? And second, is there a polylog-log-n round MPC algorithm that can color constant algorithm graphs using constant number of colors? So we can color a tree using log-log-n rounds, but for greater algorithm, we don't know how to do that. Okay, so thank you.
Our next talk is by Merav Parter. It's on distributed construction of dual failure fault tolerance distance preservers.
Yes, so I'm going to talk about distributed constructions of dual failure fault-tolerant distance preservers. So let me start by introducing the notion of distance preservers. These are just sparse subgraphs that preserve information, distance information about a given pair of nodes. Okay, so for example, assume that we are just given a single source, and our goal is to preserve distances only with respect to that source. So we don't need to maintain the entire graph. We can just compute a sparse, short sparse tree with n-1 edges, and that contains all the information about the distances from S to any other node. The limitation of short sparse trees or distance preservers is that they are very sensitive to faults. So now if a single edge, for example, fails in the structure that we computed, the tree breaks into two components and it no longer says anything about the distances in the original graph that survives. So for example, if we just add few more edges to our structure, maybe we could still say something meaningful. So our goal is to take the basic distance preservers and to augment them with additional edges, but not too many, so that they will continue to preserve information about the distances even under faults. Okay, so to say it more formally, the notion of source-wise fault-tolerant preservers is as follows. We are given some unweighted graph G and a set of sources S, and we would like to compute a subgraph H that satisfies the following. For every pair ST and for every H E that might fail, the distance in H minus E is exactly the same as the distance in the original graph minus E. So if the edge E that fails just disconnect S and T in G, there is nothing that we can do. Their distance is infinity, okay? But for every S and T, we look at the original distance in G minus E, and we would like to have the exact same distance in the part that survives. So we can always take H to be G, but we want H to be as sparse as possible. And note that by definition, this sparse graph H must contain many BFS trees. It must contain a BFS tree in G minus E with respect to each of the sources, just by definition. In the same manner, one can also define fault-tolerant additive spanners, where the only difference is that here we allow the preserver to slightly stretch the distances by an additive term of beta. Okay. So our goal in this work is to provide distributed constructions of fault-tolerant preservers. All these structures have been studied thoroughly from the centralized perspective, but not so much from the distributed perspective. And we consider the congest model. So we are very limited by the congestion. We can send only log n bits of information on each of the edges. The two main complexity measures that we have are the number of rounds and the sparsity of the output subgraph. So true trivial solutions is to do nothing and to end up with a very dense graph, maybe quadratic, or to just collect everything to a single node and to run the centralized computation, but then the running time is too large. So we would like to have sublinear round complexity and say subquadratic size of the structures. So here is a summary of our result. We start by considering constructions of source-wise preservers that are resilient to a single edge failure. Then we extend it to two edge failure, and eventually we get also additive spanners that are resilient to two faults. Okay, so here is the first result that I'm going to discuss slightly more. For the source-wise preservers, we have constructions in D plus square root Sn rounds. The prior work had a construction of just order D. D is the diameter, the unweighted diameter of the graph. So prior construction provided diameter many rounds for a single source. So a trivial extension for that will be S times D. And instead we have D plus square root Sn, which improves for many sources. And the sparsity of the graph is also existentially optimal, which is this number of edges. We also extend it for dual failures, and this is actually the first construction, the first distributed construction that can handle two faults and eventually two additive spanners with sublinear round complexity and with subquadratic number of edges. These bounds are far from tight, but I treat them as the first step to do something for two faults in the distributed setting. So I'll just say in a bit what's the challenge. The challenge is we try to build in a distributed setting a preserver, a fault-tolerant preserver that is made of a union of many BFS trees in G minus E. So we need to build simultaneously order of S times N many trees. This induces a lot of congestion because we can send every BFS send a message on every edge in the graph. So if we have many BFS trees, we send too many messages, and that's just too much. And the question is whether we can do better. And the first observation is that one can indeed have some saving just because it's sufficient to send information only for edges that appear on the shortest path from the sources to the target. But even that does not suffice. And I'll just say in one line that our approach is based on distinguishing between near fault and far faults. For all the faults near the target, we propagate the BFS tokens, but we don't have too many near faults. And for the far faults, we just handle it by random sampling. Okay, so let me just end with some open hands. In this work, we provide construction for multiple sources and one fault. The sparsity is optimal, but the round complexity might not be optimal. For two faults, we just have the first result, subquadratic size, sublinear round complexity. And for F faults, currently the setting is open for any F at least 3. Thank you.
Our next speaker is William K. Moses Jr. Talk is on singularly optimal randomized leader election.
Hi, everyone. My name is William K. Moses Jr. I'm going to talk about singularly optimal randomized leader election. Now, I'll break that title down in this talk. And this is joint work with Shai Kutten, Gopal Pandurangan, and David Peleg. So in this short talk, I'm going to do three things for you. I'm going to set up the problem. At least you'll know what this problem is about and why this paper is interesting. Then I'm going to tell you why you should care, not just about the problem, but about the long talk and about the paper. Finally, I'll give you a sneak peek at what the algorithm is. So, leader election, what is it all about? Well, there are multiple processes, and they have to work together to elect exactly one unique leader, and this leader should be known to everyone. Once this is done, the processes should terminate. Simple enough. More formally, we have n anonymous nodes, where anonymous means that they don't have unique IDs. They're connected via a complete graph, and there's congestion on the edges, which is to say messages are restricted to login bits each. Furthermore, we have something called adversarial wake-up. What that means is every node starts out asleep, and they can be woken up in one of two ways, either by an adversary or by a message. Now, we have solutions for both synchronous networks, where time moves in rounds, and asynchronous networks, where a message can be delayed for an arbitrarily long amount of time by the adversary. Now, any solution has to be measured in some way. We measure our solutions by two metrics. First, the time from when the adversary wakes up the first node until the final node terminates. And two, the total number of messages that are sent over the course of the algorithm. And as you've seen in our title, we have this word singularly optimal. This is a measure of the solution. And a singularly optimal solution is one where both metric 1 and metric 2, time and messages, are optimal up to polylog factors. Great. Now you know what the problem is. Well, why should you care? First of all, why care about leader election on a complete graph? Well, leader election is fundamental, and there are plenty of applications. Okay, but why complete graphs? Well, complete graphs are dense, and that means it's non-trivial to actually have small message complexity when solving leader election. And why should that matter? Well, solving it on a complete graph will be a stepping stone to solving it on more general graphs. That's nice. Now you should care. Now you know why you should care about the problem. Well, why care about this paper? Well, we have two solutions in this paper, one for asynchronous networks and one for synchronous networks. For asynchronous networks, the previous best result on leader election was by Singh, where he had an n log n message complexity algorithm and an n by log n time complexity algorithm. We bring both values down from n log n to n messages and from n by log n to log squared n. And remember, these are singularly optimal results. Message complexity is optimal, and time is optimal up to log squared n factor. And we have randomized in our title as well. Why? Because to break this bound and this one, we make heavy use of randomization. Like I said, we also have solutions. We also have a solution for synchronous networks. Previously, Randomized et al. Had a message optimal algorithm that took log n time. We bring the time down to an optimal value of O of 1 while preserving message optimality. Furthermore, we improve the success probability. Great. Now you know why you should read the paper. But what about the long talk? What's in it for you? In that talk, we'll have more intuition about the asynchronous algorithm, and we'll also have a brief analysis of time and message complexity. Good. I hope I whet your appetite. Now, I want to leave you with a last little bit. I'll give you a sneak peek at the algorithm, and the most important part about it. For asynchronous networks, we use a common technique, that of referees. Let's say I have two candidates, the blue and the green node. Now, each of them chooses a certain number of referees, let's say 2, and they send a message saying, hey, can I be the leader? Now it's up to the referees to say, yes, you can, or no, you can't. Basically, these referees say, make a comparison among all the candidates seen and say, this is the best. You may proceed. And so a leader is elected. Okay, that's common, that's known. What do? Well, we have something interesting going on. First of all, when you have an asynchronous network, messages don't always come at the same time. So sometimes these referees, they have to remember, the previously best seen guy was green. I told green he can become the leader. And what happens then if a candidate, say blue, later asks the referee, hey, can I be the leader? Well, most of the time it doesn't matter if blue was worse, but if blue is better, we do something kind of interesting. If the referee sees that, green was the best so far, but blue looks better, the referee says, you know, this is too much work. I'm going to offload this work. Green, you deal with this. And so the green candidate, he determines, have I already become a leader? If so, bye-bye to blue. If not, well, then I kill myself and blue can pass on. Sends this message, green will send the message back to the referee processes it and sends a message back to blue. This technique, this referee technique, combined with a phased approach, allows us to save messages. What's this phased approach? Well, essentially we say everyone is allowed to play this game to be a leader, but they have to proceed phase by phase. Instead of from candidate to leader, let's have a step-by-step approach. So they compete in multiple phases, where in each phase, the number of candidates, our candidate pool, is reduced by a constant fraction, smaller, smaller, and smaller, until after log n phases, only one leader remains. And why does this save messages? Well, we say that any candidate who's in phase I can only make O of 2 power I probes. And we show this nice degradation. So of a fourth of the candidates. The candidate pool decreases by a fourth. So if you multiply the candidates with the number of probes they make, the number of messages they send out, and add it up over all the phases, you get O of n messages. So in conclusion, why should you watch the long talk? Well, we give more intuition about this algorithm. Why should you read the paper? In addition to that, in addition to the asynchronous network algorithm, we have a tightly singularly optimal algorithm for synchronous networks. And of course, what's left to do? 3 open problems remain. Well, they did remain when we finished this paper. One is, and by the way, these open problems are all for asynchronous networks. The first is to reduce the time. We took log squared n time. Can we do it faster? The second is, can we have a singularly optimal deterministic algorithm? The final one is, can we bring these results up to general graphs? And so I just want to leave you with 2 things. We were actually able to make progress. First, we reduced the time down to log n, and we actually have a singularly optimal algorithm for general graphs. So with this said, I conclude my talk. Please watch the larger talk to know more. Thank you.
And so our next speaker is going to be Ami Paz. And the title is Models of Smoothing in Dynamic Networks.
As I said before, this is a work on model of smoothing in dynamic networks with Uri Meir and Gregory Schwartzman. In this work, we study one simple and basic problem of flooding when we have one node in a network that wants to propagate information to all the others, just by forwarding the information again and again until everybody learns the information. In a static network, this will take diameter time, even regardless of the starting point. But what happens in dynamic networks? So we know it's not hard to show that n-1 rounds are sufficient, regardless of the structure of the network, as long as it's connected in all rounds. And this can indeed take n-1 rounds. Of course, if the diameter is n-1, let's say on a path, but also if on graphs with constant diameter, you can still build a structure and it will take n-1 rounds to propagate the information to all the nodes. So we know that flooding in adversarial networks, like if the network changes the worst case it can take up to n-1 rounds, even with low diameter. If the network was random with some reasonable model of randomness, this will probably take only log n time. And we were wondering what happens in between if a network is not totally adversarial but not totally random. And to this, we use the model of smoothed analysis, or actually we define models of smoothed analysis. These are models that allow you to model system that is adversarial, that is the worst case behavior, plus some random perturbation on the adversarial setting. So the idea of smoothed analysis was presented by Spillner and Tang to understand sequential centralized algorithms for the simplex algorithm specifically, that we know that behaves in practice much better than theory would expect. And this was adapted in disk, I think, 3 years ago by Dinitz et al. This is the journal version in 2018. And this was to distributed dynamic networks. And we follow up on their work. So Dinitz et al. Presented a model of integer noise, which says the adversary picks a sequence of communication graphs, GIs. And then for some smoothing parameter K, the real graph on which flooding happens or other problems happen is picked at random for a ball of Hamming radius K around this graph. So it will look something like that. The adversary picks a sequence of nodes, a sequence of communication graphs. Each of them is being smoothed, and then the algorithm is executed on the smoothed graph, on this sequence of graphs that are not exactly what the adversary would like to do, but similar to them. And under this model, they show that flooding takes n to the 2/3 over k to the 3rd round, where k is the smoothing parameter and is an integer. And this is already very interesting because there is a polynomial gap between no noise, k equals 0, where flooding can take n-1 rounds, as I mentioned, and even one edge that is being added or deleted in each round, which makes flooding takes only n to the 2/3. So we were very curious about this gap, and on other questions like what happens if the adversary is adaptive and can see the smoothed graphs so far before choosing the next communication graph. And what happens if the noise is responsive, on which I'll talk in a minute. So first of all, we extended the model of Dinitz et al. By presenting an adaptive adversary who sees the communication graph and the smoothed graph, sorry, before choosing the next adversarial graph, and then it's being smoothed again. The adversary sees what happened so far, choose the next, and so on. And we also extended this to the case where k is fractional and not just in integer. Next, we talk about proportional noise. That is, the number of smoothed edges in the network depend on the number of changes the adversary performs. So if the adversary doesn't do any change, there's no reason to have random edges all around. But if it does make a lot of changes, there will be a lot of random edges. If it makes a few edges, then also a few random changes by the smoothing process. And finally, we address a model of targeted noise, who is a bit more strict than the previous one, who says, and here we say, the smoothing, the random edges that come or go, are only subset of the edges that are changed by the adversary. If some part of the graph doesn't change by the adversary, why should you have random edges being added or removed there? And for all these models and several others that I didn't mention, we have results. And the most interesting thing here is maybe not the table itself, but the fact that each specific model that may seem similar to one another have very different results. And one other thing I would like to say to resolve the question I mentioned before is what happens with k. When k is fractional, and specifically we define it for any fractional k, but specifically for k between 0 and 1, we have, say, an edge that it's added or removed with probability k. And there we see that the flooding time is still n to the 2/3 over k to the 3rd. So we extend the result also to k values between 0 and 1. Theirs was only for integers k values from 1 and on. And so just to conclude, we show that there are many interesting models of smoothing and have different properties. So if you want to apply smoothing for real-world system and understand how it will behave, you should really understand well what's happening in your specific system. And the open problems are, first of all, to study other problems, say random walks or heating time of random walks. And know that here the algorithm, just like in flooding, is passive. You don't really have an algorithm. You just, what happens, happens in the flooding or in random walks. Other problems are like load balancing or being in a minimum spanning tree. And here we also have an algorithm that may depend on the flooding, on the smoothing, and the adversary may or may not see what the algorithm does and so on. So it gets much more complicated. And other type of questions are defining even more models of smoothing that will be driven from real world applications or systems that we want to understand. So I'll stop here and address you to the long presentation. Thank you.
So the question is, do you know how that works with the semi-random setting of Santa Vazirani? Basically, you have an adversary and the choices have a probability of being reversed. You have a noisy adversary. Is that one of your settings?
So yes, the last that I mentioned was indeed a setting that is similar to that, in the sense that, yeah, some of the changes are being reverted. But it's an interesting question. I'm not familiar with this work, actually, so I cannot tell you more about the relation between them. But here, I mean, there is an adversary in our model that I'm not sure what is semi-random setting that you're addressing, but I think maybe they don't have an adversary, so it's probably different.
All right, well, thank you very much. And so our next speaker is also a previous speaker, or we have a talk on distributed planar reachability and nearly optimal time by Mirav Parter.
So we're going to see distributed algorithms for computed reachability in planar graphs, and we consider the standard congest model. The two important parameters that we care about in the network is the diameter, is the unweighted, undirected diameter of the graph, and is the number of nodes. And as usual, we can exchange log and bits of information between each of the neighbors. And note that even though in this talk we are going to discuss directed graphs, still the communication graphs are going to be bidirectional. So the key complexity measure is the number of rounds that it takes to solve the problem. So let me say a few words about this sub-area of distributed algorithms in planar graphs. This sub-area was initiated by Gavari and Opler by a sequence of 2 works. And the major goal is to provide algorithms, improved algorithms that enjoy the planarity of the graph. For many global graph problems, we have a bad d plus square root n lower bounds for general graphs. But the hope is that we can avoid this lower bound when the graph is planar. And indeed, we have improved algorithms for many global problems. And today we are going to consider reachability problems. And this is the first work to consider that. Okay, so here are the 2 main results. The first result, consider the classic single source reachability problem. In this problem, we are just given a planar graph, a planar directed graph, a single source S, and the goal is to identify the set of all nodes that have some incoming path from S, okay? So these are all the nodes that are colored here in yellow. And for that, we have an order D, order diameter round algorithm to compute the single source reachability, and this improves the implicit D square round algorithm from prior work. We also consider maybe the most general reachability problem, which we call strongly connected components identification. So here the goal is for all nodes to output some unique identifier so that all nodes that lie in the same strongly connected component have the same identifier. Also for that, we have a diameter round algorithm. And for that problem, we didn't have a prior algorithm, not in planar graphs, but not also in general graphs. Okay. So the key tool that we are using is a tool that has been developed in our prior work. It's what we call bounded diameter decomposition. It's a way to decompose the graph, the planar graphs, in a recursive manner by computing planar separators. Okay, but this computation is very much suitable for the distributed setting. So at the end, what you get is just a tree of the recursion. All the trees in the same recursion level are nearly edge disjoint, and their diameter is roughly the same as the diameter of the original graph. So this allows us to solve many problems in some divide and conquer manner, as we usually do in the centralized setting. Okay. So in order to solve the single source reachability problem, the key problem that we had to solve is what we call the computation of reachability preservers. So here is the key computational task. At every step of the recursion, we have some subgraph that, let me call it G prime. And the goal is to compute all the reachability between all the separator nodes. We have roughly diameter nodes marked as separator nodes, and we would like to compute the reachability relations, whether they have incoming or outgoing path from one to another in G prime. The main challenge here is that this graph, this preserver, might have this square many edges, because maybe there is a path between every 2 nodes in the separator nodes, but we have only d many rounds. So what we want to do is to compress the information in the reachability preserver into roughly d many bits. So we need some local compression scheme so that every node will send only few many bits plus additional diameter many bits. Once this is sent, all the nodes can compute the reachability preserver. So it's really about a local distributed way to compress reachability information between separator nodes in a planar graph. So this is the story of this algorithm. So overall in this work, we have several reachability algorithms for single source. Also, we can support multiple sources provided that they all lie on a single face, and we can solve the strongly connected component identification problem. Let me just say that one of my motivation to start studying this problem was actually another problem, which is the single source shortest path problem in undirected graph. For that problem, the best round complexity is this square, and I'm very interested to know maybe one can provide a diameter round algorithm. And because there is a connection between reachability problems and single source shortest path problems, my hope is that this work might be the first step towards obtaining any improvement on the SSSP problem. Thank you.
Kind of a naive question. What's the story for deterministic algorithms for this
Yeah.
problem?
Yeah, it's a very good question. I think for some reason, which I'm not sure that it's very much, maybe it can be avoided, but our basic separator algorithm that we currently have to compute a separator are randomized. And because we are building on top of that, our algorithm are randomized, but I would not say that it's a true randomness. I would imagine that with some work, this randomness can be avoided. It's not, you don't feel that it's really essential in this kind of computation.
So there's no deterministic lower bounds that are a lot larger than.
No, I would believe that it should be diameter, maybe with some polylog, yeah, but I would imagine that one can de-randomize the separator algorithm, and once this is done, we don't have extra randomness beyond that in the algorithm.
Yeah.
Thank you for the great talk, Manab. So you mentioned that at some point about this result about strongly connected components, and that round complexity depends on diameter of the graph. So I was wondering whether there is a hope to get a better round complexity if you know that diameter of strongly connected components is much smaller than diameter of the full graph.
Mm-hmm. I think that yes, because then what you might do is just run some ball carving thing and just try to work in a smaller ball to capture the entire connected component. You need to add some piece to know that you reach to the level that you capture the entire thing, but I think that you can do that maybe. So I would not rule it out. Yeah, it's a good question. Maybe you can tighten up to be depend on the diameter of the strongly connected component. Yeah.
Thanks a lot.
Mm-hmm.
Yeah. All right. Well, thank you very much. And let's move on to our last speaker. So will be Ard Castrati. And this is a brief announcement on multi-threshold asynchronous reliable broadcast and consensus.
Hello, today I'm going to give a presentation of a joint work with Martin Hirt and Chendar Liu Zhang on multi-threshold asynchronous reliable broadcast and consensus. So the model we consider is the traditional model. So the network is complete, asynchronous, and with public channels. The adversary, on the other hand, can corrupt some of the parties, which we denote by F, is Byzantine, and we assume the adversary has unlimited computational power. So we argue about security in information theoretic sense. So multi-threshold broadcast is a generalization of broadcast and is basically defined by considering separate thresholds for each of the properties. More concretely, what we want is if the number of corruptions is below some threshold TV, then we want the protocol to guarantee validity. So which means if the sender is honest, every recipient that outputs the sender's message M. Then for consistency, now we have a different threshold, and as long as this number of corruptions is below than TC, then we want consistency, meaning that even if the sender is dishonest, if the recipients output, then they output consistently. And finally, we have the termination with, again, with a separate threshold with TT. And here, of course, we cannot hope more than partial termination because of the asynchronous setting, meaning that if the sender is honest, we require the parties to eventually terminate. But if the sender is dishonest, then what the best we can hope for is either no one is going to terminate or everyone terminates. The same idea applies now to consensus. So here again, we have separate thresholds. As long as the number of corruptions is below TV, we want validity. So meaning that if the parties have pre-agreement, then they keep this value. The consistency is the same. So in consensus basically means that starting with some put xi, the parties that output some value y, as long as it is consistent among the parties. And finally, if the number of corruptions is below than TT, then we require termination. But here we distinguish between two types of termination: almost surely terminating consensus, where the parties are required to terminate with probability 1, and the other case where they are required to terminate with probability 1 minus epsilon. So basically, if they start with some input xi, eventually they output output epsilon I. Now, our results give a characterization of what is possible on these primitives. So we show that multi-threshold broadcast is achievable if and only if maximum of TC and TV plus 2TT is smaller than N. Worth mentioning here is that all these properties are kind of independent to each other. So there are cases where you can design in this protocol where termination is above maximum of TC and TV, whereas many previously proposed solution kind of the termination property depends on the consistency. And here is the theoretically challenging part was kind of to make sure that parties terminate even though they don't achieve consistency. For multi-threshold 1 minus epsilon consensus, we also have a complete characterization, and we show that this is possible as long as the same as in broadcast, maximum of TC and TV plus 2TT is smaller than N, and in addition 2TV plus TT smaller than N, which mainly comes from the definition of consensus itself. Finally, for almost surely consensus, we show that this is possible under the same bounds. In addition, we also require TT smaller than a third. Whether this is optimal is left as open. However, we give a construction by assuming a global coin, which doesn't require this bound and thus is also optimal. Thank you very much. If you have any questions, I'd be happy to answer you.
Yeah, I was wondering whether you can provide any intuition for any of these bounds. Pick one of them. Like
yes.
What the numbers mean. Or how they
yes.
work.
So for example, for broadcast, this is kind of one can see it's a generalization of the single threshold case which is possible as long as T is smaller than N third. So if you think about this impossibility proofs, why consensus, for example, broadcast doesn't work, then one of the subsets you can think of as the size of maximum of TC and TV, and the other are 2TT. And then one can show that the part by similar arguments that these bounds, then it's impossible if you kind of have maximum of TC and plus 2TT to be bigger than N. For consensus, it's again very similar. So, for example, this bound is now a bit different. So, because of the asynchronous, the parties agree cannot wait for more than N minus TT input, right? So, because of the termination requirements. But on the other hand, consensus is not achievable if more than half of the parties, for example, in a synchronous setting, you need at most, the number of corruptions can be at most than half. So there where you have like where the 2 comes from. So if you think about only a subset with sizes N minus TT, then their kind of consensus is achievable only if half of those parties are corrupted. So otherwise validity cannot be guaranteed, right?
Okay, thank you.
All right, well, thank you very much for very nice talk, and I'd like to thank all of our speakers for being so well organized. This was a joy to run this session here, and this concludes our session.